Here's sample test 3, problem number 1. In the circuit at left, what is the equivalent capacitance of the network if C1 is 20 microfarads, C2 is 10 microfarads, and C3 is 30 microfarads? So we have 20 microfarads, 10, and 30. You know, wherever we have line of wire, we can either add wire or subtract wire. It's just wire, and we're assuming it's resistance less. So really where these two wires come together is a node, and where these two come together down here is a node. They're actually connected on both ends, so they are in parallel. So we can actually redraw this circuit just a little bit to clearly show that these two capacitors on the end here are in fact in parallel. And here's our battery. So we have 18 volts here, we have our 10 and our 30 in parallel, and then we have our 20 over here. So the parallel combination adds together, and now this circuit looks like this, with 40 microfarads over here, 20 here, and then we have our battery here, 18 volts. Now the 20 and the 40 are not in parallel because of the battery, so they are in fact in series because there's one line of circuit going through both of them, and hence we have a series combination for our equivalent capacitance, and it's two of them. So our C equivalent is going to be product over the sum, and that's going to be 20 times 40 over 20 plus 40, which would be 800 divided by 60, or 13.3 microfarads. So that is the equivalent capacitance of our whole circuit. Basically our circuit could look like one equivalent capacitance with the battery, 18 volt battery, and this one C equivalent of 13.3 microfarads. Sounds good. So that's part A. Part B, what is the charge stored by C1? Well, the only thing we know the voltage on is the equivalent capacitance. So we know we can calculate the charge on the equivalent capacitance. That's equal to CV, or C equivalent, times its voltage. And so that would be 13.3 microfarads times 18 volts, which will give us 240 microcoulombs. Now that is the charge on this equivalent capacitance here. But we do know that things in series have the same charge, and they have the same charge as their equivalent device. So the series combination of the 20 and the 40 right here, those two capacitors will have the same charge as their equivalent capacitance, and hence the charge on the 20 microfarads will be equal to the charge on the equivalent capacitance of that series combination, which is 240 microcoulombs. And that is C1, so that is the charge on C1. So the charge on C1 is 240 microcoulombs. I guess I could call that just Q1. Let's do that. Q1 is 240 microfarads. Oops. Part C, what is the energy supplied by the battery? Now, for energy stored in any particular capacitance, we have 1/2 CV squared if we know the voltage across that capacitance, or the charge squared over 2 times C. Those are our two most common things because we're usually going to either know a charge or a voltage across something. Now in this case we could figure out 1/2 CV squared for all three of these capacitors, but we don't know all their voltages yet. Or the equivalent capacitance should represent the whole circuit. So the energy stored by the whole circuit will be the energy stored by our equivalent capacitance. And that would be 1/2 C equivalent times its voltage squared. That's going to be 1/2 times 13.3 microfarads times 18 volts squared, which is going to give us 2,160 microjoules. We still have the micro in there. Or we could write that as 2.16 millijoules. So the energy stored by the whole circuit is 2.16 millijoules. That must come from the battery. So that is indeed the energy supplied by the battery, 2.16 millijoules.